Section 2 of Chapter 7 is very similar to Section 1. So this will be a shorter lesson because we've learned it all. We're just going to kind of turn it a different direction. So now we're going to graph exponential decay functions. Yesterday we graphed exponential growth functions, and now we're going to decay. So sometimes things like money in the bank will grow. However, sometimes there's a decay. We talked about population growth. Sometimes the population declines. So in this case, decay functions. And the graph actually, now in this case, the model, the function looks the same, exactly the same. Y equals a to the bx, b to the x power. However, the difference is this. The a still needs to be greater than 0, so we still have to stay above the x-axis. But b is between 0 and 1. So in other words, b is going to be a positive fraction. All right, so if b is between 0 and 1, it's a fraction. So if b is a fraction, then what's going to happen is when we have that the 0, 1 point and the 1b point, if b is a fraction, it's less than 1, so that b point is going to be lower than this y-axis point, and so the graph is going to then look like this, and it's going to be decaying, and it's still going to be coming, it's still going to come close to the x-axis. The x-axis is still the asymptote. Remember that word from yesterday. The x-axis is the asymptote, and so the range is still going to be anything greater than 0 for the y-axis, or for the x. The x-axis, sorry. So now that we know what the parent graph looks like, let's graph some of them. So the first one we're going to do is y equals 1/2 to the x power, and you're just going to have to bear with me for just a little bit. Let's do some points, and then I'll show you the 2-point shortcut here. So if we're taking 1/2 to the -3 power, remember the negative power flips it, and then 2 to the 3rd power is going to be 8. And if we have 1/2 to the -2 power, it's going to flip that fraction. So the 1/2 becomes 2 over 1, and then to the 2nd power becomes 4. And if these steps, if I'm not clear enough, and if I'm doing too much, make sure to come to me in class and ask me, now, where did these numbers come from? Either that or look at it yourself and work it out and figure it out. Write down the different steps. Because 1/2 to the -1 power is going to flip it and make it 2 over 1. So now we have 2. 0 power, remember anything to the 0 power is 1. So that's where your 0, 1 point comes in. And anything to the 1 power is itself. And then if we take it to the 2 power, it's going to be 1/2 times 1/2, which simply gives us 1/4. So when we plot these points, negative 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8 is up here somewhere. -2, 4. -1, 2, 0, 1, 1, 1/2, and 2, 1/4. It gets very small very quickly, and so then our graph looks like, oh, here I go again, trying to, oh, not so bad that time. Looky there, practice makes perfect. So there you go, practice some more. All right, so the decay function, you can see, looks exactly like the parent function, the parent graph. It starts up high, and then it comes down very quickly, and it gets smaller and smaller and smaller very quickly. And so that's what the graph looks like. So knowing that, if you have 2 points, you can combine those two and make yourself a graph. So remember, the A is going to be your, when you multiply something by that first part of the graph, if you have an A, that's going to be your y-intercept. And this is stuff that we learned in 7.1. So if you're not sure, go back to those notes and see, where does this come from? The H, remember, is a horizontal slide. And the K is your vertical slide. And then the A is also, so the A is not only your intercept, but A is also, it tells how much it's going to shrink or stretch. Okay, so let's just go right into it and let's just do some. So if y equals 3 times 2/3 to the x power, we know that if we put in the 0, that's going to make this equal to 1. So 3, remember, is our y-intercept. So 0, 1, 2, 3, there's a point there. And if we put in 1, so 1 to the 2/3 power to the 1 power, 2/3 to the 1 power is just 2/3 times 3 ends up with 2. So 1 over 2 up. So now we're going to start high and go through those 2 points and get close, and probably closer than that, close to our x-axis. And that's it. All right, same thing here. Now in this case, our a is 0, or our a is negative, which means it's not greater than 0. So this is going to be one of those that's not an actual decay function. But we can still graph it by using what we know about exponential functions. So we've got, if we use 0 as our x, so that makes this just -2. So 0, -2 is 1 point. And then if we put in 1 for here, we've got -2 times 3 over 4. And so this reduces down and we've got 3/2, -3/2. So 1 over -3/2 is 1.5, so right about there. And what's happening with this is a decay function that is flipped. So if you take this function and flip it, then what's going to happen is this is still the asymptote it's going to get close to, and it's going to start somewhere down here. And for me, actually, it's easier to go backwards when I'm drawing the line. So that's what that graph is going to look like. So the negative a is going to flip it and mean that it comes from very, very, very far negative and comes up almost to the x-axis. All right. Let's do one with a slide because this is too easy. Here we go. Y equals 2 times 1/3 to the x minus 2 power plus 1. And if you'll remember, the steps are, first, just graph it without the h and the k. So we're going to just graph 2 times 1/3 to the x power. So we just need those 2 points. So let's do that. 0, 0, 2 is our first point when we're ignoring this h and the k. And then if you put in 1, 2/3 is what you end up with. 2 times the 1/3. So 2/3 is right about here. All right, so our function, or our graph, our decay graph is going to look like this, right? Because it matches the parent graph. All right, but we're going to slide it. And this is because, remember, with the slide, the h is negative. So this is going to be 2, 1. So our slide is going to go horizontally 2 and vertically 1. So it's going to go 1, 2 over, 1 up, 1, 2 over, 1 up. And now because we've gone 1 up, instead of our asymptote being the x-axis, it's now +1. So we're going to approach this but not cross it. And then it's going to go way up like this. So now our asymptote is y equals 1. And so let's see, what do we do here? So now our domain is all real because it's any of the x's, right? And our range, can you even read that, I wonder? Our range is going to be anything greater than the 1. So y has to be greater than 1. Okay, you see where I got that? Hopefully. All right, let's do one more thing. Let's do exponential decay model. So that's graphing it. Let's put it into, all right, can I say this? And now it's on video. I really prefer to do algebraically than graphically. Ha ha ha. All right, here we go. Now the truth is out. So the exponential decay model, and this is what I was talking about with sometimes the population decays. There's less people. We're actually going to do one with the value of a car today. So The exponential decay model, you may say, oh, that looks very familiar. Well, it should. It's actually very, very, very similar to the exponential growth model. The only difference is I erased this plus and made it into a minus. So what's happening is you start with your initial amount, whatever you start with, and then you take 1 because that's the amount you started with, and you subtract that rate, the rate of decay instead of a rate of growth. So that's why you subtract it instead of adding it. And then take that amount to the and raise it to the power of how many years you have. This is t in years. Okay, let's show you what I mean. This is another case of if you know that formula, you're just going to use the formula. You need to know what pieces to plug in, and then you've got it made. Here we go. So our formula is y equals a 1 minus r to the t power. So in this case, we've got a new car that costs $35,000. As soon as you drive that brand new car off the lot, it starts losing value, and exponentially it loses value. So it loses very, very, very quickly at first, and then as it gets closer and closer to 0, then it peters out and it doesn't lose it quite so quickly. So this is a good example of exponential decay. So we've got the car cost is the initial amount, so that's the $35,000 is our A. 1 minus the rate is the 15% per year. So 1 minus 15, we can even just do that in our head. So 15 is, so 1 minus 0.15 is 0.85. To the t power. So the first thing we wanted was just model the decay amount, model the decrease of this car. So there it is. That's how you model it. And now if we want to know what is the value of that car, so I paid $35,000 for this car off the lot. In 4 years, I don't like it quite so much, I want a new car. Well, in 4 years, how much is that car worth? Let's look and see. We can simply put it into the formula. And our time is 4 years. And so this is where you'll go back to your calculator and put in 0.85, take that to the 4th power, either using your caret key or that x to the y power. Take that number, multiply it by 35,000. See if you can do it before I find it, because I did it already. And you will find that, and be careful because you don't want it to, it's not equal to, because you're going to round it. It's roughly equal to, and I get $18,270. Wow, that's a far cry from the $35,000 that you started out with. This is why I buy used cars. Here, let somebody else take that hit, because it is going to decrease after that, but you'll find if you plug in that same number after 6 years or after 8 years, the difference between the 18,000 and then the difference between 4 years and 6 years isn't nearly as big, because that exponent, the first few years take the hit quicker. All right, so that's how exponential decay works. And you could graph this also and see, well, in this year, how much is this going to be cost? Or you can simply put it into the formula. All right, I think that's all I have for you today. Quick and easy. I'll see you next time.